extend here. First, a very simple one, a not very exciting one, and then an exciting one for you to go to the exercise part. And here is the general part. There are some rules for how to deal with means and variances in general. So I'm very general now. Actually, I'm so general, so what I'm saying now is something that is valid for both discrete and random distributions. So it's a general stuff that comes up here for means and variances. And here the first and boring result comes. It has to do with the possibility of changing from scale to scale in the first. For instance, if we measure something in Celsius and you want to change to Fahrenheit, well, if I did a large study to 2 millions to capture a mean and a variance on the Celsius scale, would I then have to redo the experiment in the US for a few millions to get the mean and the variance on the Fahrenheit scale? No, you do not have to spend the millions. You can use your math skills and realize that these two rules rule. For instance, the mean rule. If I'm interested in the mean or the expected value, we use that interchangeably, of a linear function of some random thing, x, I can apply the same linear function to the mean of x, right? So if I know the mean on the Celsius scale, I could find the mean on the Fahrenheit scale by the obvious solution. Mathematically, this is a rule going for integrals. Right? This is, say, similar rule applies to the integral, whenever the integral exists. And since we also have that, here's maybe the more interesting one. Because I think the first one here, every one of us would have done, not even thinking about that there would be a rule to support it, that would just be common sense again. There is a variance rule that says, how can I find the variance of the linear transformation of some random thing? If the idea is that I already know the variance of x, then I transform x. What is the variance of the transformed, of the new thing? Well, remember my normal distributions? If I shift it by b, the thing that I shift the distribution by adding a constant does not change the shape of the distribution, does not change the variance. That's why the b disappears. However, if I multiply, if I have something between -2 and 2 and I multiply it by 1,000, then of course it's not more between -2 and 2, now it's between -2,000 and +2,000. So when I multiply by something, the variance is multiplied by the square of that, which means that the standard deviation scales up with the number, if you want. The standard deviation would be just a times the standard deviation of x. I didn't put that explicitly. So a little silly example, that's the one we're not going to spend many seconds. It's just exemplifying the little rule that I gave you that we can plug in. I'll not even spend more seconds than that because I'm getting more and more tired of this example. I'd much rather talk about this little more complicated but also much more important thing coming here. So, what if I have several pieces of information? I have several random variables. And in statistics, that's exactly what we always have. And next week's statistics is really starting. So this is, wake up and listen in now, right? This is a step towards what's going to happen in the rest of the course. By a little example. The mean of a linear combination of a lot of x's. What is a lot of x's? I mean, it could be the height of guy 1, the height of guy 2, the height of guy 3. That could be the different x's, right? So that's what we have in statistics, numbers coming from many sources, many observations. The mean of a linear combination, and now this is a bit of math generality, a linear combination could also be the sum or the mean, right? Because the sum, then all these a's would be 1, or the average, all of these a's would be 1 over n. So this is a math expression of something that also would apply to the sum or the mean. But it could also be a weighted sum or the weighted mean, and the math would still give us the result. The mean of something is the same something of the means. Well, not still very exciting. This is slightly more exciting. And you can recognize the little thing from before, but in an extended version, the variance of a linear combination of many random sources, many random stuff, is a linear combination of the variances, but using the squares of all these a's. This is an extremely important rule, and we jump to the final example of today, trying to make a point about this little rule.